Hello students, welcome back to another lecture in our course Environmental Modeling and Simulation. Today we are going to continue our discussion on the emission of pollutant or the contaminant that we are tracking through a stack, through a chimney. We are going to continue our modeling, and in the previous class we talked about diffusion and how it follows Fick's law, and then we derived a very simple mass in mass out conservation equation only accounting for diffusion. But if there is bulk action due to wind, then we need to also account for wind. Of course, when there is no wind, just the diffusion equation is how we need to proceed. I want you to note one thing. So far in our discussion of this contaminant moving through the fluid air coming out from chimney did not have anything to do with the properties of air. It did not have anything to do with even the kind of contaminant that is coming out, except for the very simple assumption that there is no chemical reaction that is happening, the contaminant is not transforming into either secondary contaminant or degrading into benign or even more harmful products. As long as that assumption is met, the model that we are deriving here, the principles we are applying here are also applicable for any other fluid, any other kind of contaminant. A simple example would be a contaminant in the groundwater will also follow the same principles. It will also spread via diffusion and via bulk action. If I take chalk or some other marker or compound and sprinkle it in a moving river or a pipe that has moving water in it, it will also be transported both due to diffusion and dispersion. In all cases, we are going to take a look at the control volume of a small minuscule parallelopiped with dimensions del x, del y, del z. We are first going to look at diffusion and then we are going to look at bulk action. Put them together, we will get dm by dt for that particular parallelopiped, and then we will integrate it, use our boundary conditions to derive the model. Now in this class, we are going to focus on bulk action. The bulk action happens due to wind. Of course, we have designed our coordinate axis so that the x axis points in the direction of wind. However, even when the general wind is moving in x direction, there will be some bulk action happening in y and z direction. So we are totally going to incorporate all of them. Now let us take a closer look at how bulk action looks like. So bulk action, now this is our parallelopiped. And the directions are x, y and z. So del z, del y, del x. So let's say we are talking about x direction. So the formula that we are going to use for x will be very similar to what we use for y and z. So let's just focus on x and then we'll write similar equations for y and z direction. Now in x direction, the bulk action will happen because of the movement of wind or whatever transportation cause is. Let's say in case of groundwater, it is the flow of groundwater. In case of pipe, it's the flow of water in pipes. In case of air, it's the wind. So the direction of the portion of the wind that is perpendicular to this plane, this first plane is having the area del y del z, and it is in the direction of del x, it's in direction of x axis. So this is mass coming in because of bulk action, and then the mass leaving here will be mass out because of bulk action. When we subtract mass in minus mass out, so basically we want dm by dt in x direction, and that will be mass in x direction minus mass out in x direction. That is what we are going to do. Now let us take a careful look at how transportation will happen due to bulk action. Let us say the ambient concentration or the concentration right around the parallelopiped of the contaminant is given by C, capital C. And let us say the wind which is carrying the contaminant in x direction through del x, through del y del z surface, first here in this surface is u, the velocity is u. So we know that the concentration C moving with velocity u and the area that we are dealing with is del y del z. So mass coming in is C u del y del z. This is dm in by dt. Now we need to find, this is at this particular position, so let us say this position is x. So mass in dm by dt at x, right. Now we want to find out what is happening at x plus dx here in this surface. Let me use a different highlighter. Now we want to find out the bulk action of mass which is in the direction of moving out of the parallelopiped through the highlighted yellow surface. What we have right now is the incoming mass here from this warm gray, reddish gray surface. Okay, so to find out dm by dt, the bulk action flow of mass at this location, notice this location is x plus del x. So at x plus del x location, once again we will take refuge in Taylor's theorem, excellent for expanding things. We know that del m by del t at x plus del x will be given to us like so. Dm by dt at x plus del x, so the distance that we are moving, and then dm by dt at x derivative, and then higher order terms. As long as this is not 0, we can ignore the higher order terms. So now what we are left with is mass out at x plus dx is given by, so this is here, I am just going to write dm by dt x because we are going to subtract them. Now plus del x and then derivative of this here. So basically since we are moving in x direction, it is going to be derivative with respect to x of cu del y del z, and this is what we are going to ignore. So what we want to find out is net mass that stays. So what we want to do is mass in minus mass out, like we discussed here. So del m by del t in x direction will be mass in minus mass out. So mass in minus mass out, bring the mass out to RHS, take this portion to LHS, and what we get is minus del x. Del u, del z are constants, we can take them out. So this is just the volume of the parallelopiped, and then Cu. Okay. This is in x direction. We can write similarly for y and z directions. Let us go ahead and write it. In y direction, so let us summarize first. And notice we are only talking about bulk action now. We are going to put together the diffusion and bulk action in a bit, but right now only the bulk action. In bulk action, in x direction is minus del x del y del z del by del x Cu. Let me confirm, there we go. Now similarly in y direction, is going to be del x del y del z. Notice that this remains same. Now I am assuming, not assuming actually, I am saying that the velocity of wind in x direction is u, velocity of wind in y direction is w, velocity of wind in z direction, sorry not w, yeah, is uvw. So let us make this v and this w. Okay. So in y direction the velocity of wind is v, so I am writing v. Now in z direction the bulk action dm by dt due to bulk action can be similarly written as minus del x del y del z Cw by del z. Alrighty. We add up the dm by dt in all three directions due to wind, bulk action in x, y, z to get the net dm by dt due to bulk action, and that turns out to be dm by dt in the parallel of pi due to bulk action is equal to minus del x del y del z plus okay, this is what we have here. Now we are going to put together our equation for diffusion and for bulk action together. So the equation for our diffusion was, so dm by dt due to diffusion, so dm by dt due to diffusion are now notice one thing, there are assumptions that we have made. One of the assumptions is that the diffusion constants remain constant with x, y and z. So in x direction is going to be dx, in y direction is going to be dy, in z is going to be dz. That is the reason why dx, dy, dz could come out. Now all these assumptions that we are making, they may or may not be true for your environment, for the kind of matrix you are modeling the flow of contaminants in. In that case, what is important to remember is, do not make that assumption. Then just if let us say dx, dy, dz are not constant in their respective directions, let us say dx is a function of x, in that case do not take dx out as common. So in that case you will still have dx in here inside the derivative. If it is constant, take it out. If dy is constant but dx is not, keep dy out but keep dx in. So do not assume. If some assumption does not work for you, just do not make that assumption and proceed from there. Now of course your end result will look different, your model will look different. The other thing I want you to note is that so far we have not limited ourselves by the fact that the fluid in which the transportation of contaminant is happening is air, even though the title of the lecture says air, but the dispersion is not happening. This same principles will apply whether it is happening in water or any other kind of fluid. So this is actually the basis of most transportation models. Most transportation models will ask you or will require of you to find out the transportation of your contaminant or compound due to diffusion, due to bulk action, and then to put them together. So that is what we are going to do now. So very important to note, even though this is headed towards Gaussian plume for smoke coming out of chimney, so far it is relevant for all kinds of transportations of contaminant happening through all kinds of fluids. And the thing you need to remember is dispersion is equal to diffusion plus movement, transportation due to bulk action, which is what we are going to do now. Dispersion is equal to diffusion plus transportation due to bulk action. Okay, so let us put this together. The net dispersion is basically transportation of your contaminant, and we know it is happening due to random molecular motion, which is diffusion, and due to bulk action. We are going to put them together. The net motion transportation of your contaminant is going to be given by the summation of these two. Oh, I forgot one thing here. That is common, del x by del z. Very conveniently forgot the volume term. Okay. So let us take del x del y del z common, and then we have, let us write the diffusion terms first because they are positive. Please write down, take notes, try to do this yourself. That way you will understand this better. It will be more interesting if you try to do it yourself. And now we will put the bulk action terms. Remember, we have taken del x del y del z common from both of these. Okay, we have gotten the right hand side of this equation in place. Of course, we are going to make some assumptions, and we are going to make many assumptions actually. But now let us look at the left hand side of this equation. In left hand side, we have the net movement of net transportation of contaminant that we are targeting through both diffusion and through bulk action. So, how do we model that? We look at it as simply as dm by dt. So, what we have been doing here is that net dm by dt is equal to dm by dt due to bulk action plus dm by dt due to diffusion. So, basically on left hand side what we have is dm by dt, as simple as that. If you remember from our previous lecture, dm by dt is basically mass can be written as product of C and V. So, the left hand side of this system of this equation can be written as dCV by dt. Now, we are assuming, remember we are talking about a parallelopiped, we are not talking about the whole volume of the plume, we are talking about the parallelopiped, and the parallelopiped's volume is constant, it is del x, del y, del z. So, we can take V out of the derivative and this becomes V dC by dt is equal to del x, del y, del z into dC by dt. So, this is our LHS. Alrighty. So, now let us put our left hand side and right hand side of the equation together. So, we have del x, del y, del z, partial derivative of concentration with time is equal to, the reason I am writing partial derivative not dC by dt is because we know that the C is changing with x, y and z. So, it has to be partial derivative. Alright, it is equal to this long equation here. Okay. Now, del x, del y, del z on both LHS and RHS can cross each other. Clearly, the volume of parallelepiped is not 0. It is very small, but it is not 0. So, now we have del C by del T is equal to all the diffusion terms here. Now, since notice one thing, since okay, let us just write it down. It looks like a very lopsided equation with very small LHS and very big RHS. So, I want to take some terms from RHS and shift them to LHS. Minus all the bulk action terms. So, what we can do is we can take these terms here and move them to LHS. So, let us do that. I am not writing these two terms, but they are here. So, now we get del C by del T plus okay, now it looks like a more balanced equation. Okay. So, now in this system we have arrived at a very basic equation for transportation of contaminant through any fluid. The only assumption we have made is that the diffusion constants are constant in the direction. Dx is constant, dy is constant, dz is constant. They are different from each other, but they are constant. Now, we do not have to make this assumption. This is your universal contaminant transportation model through any kind of fluid. Now, we are going to make it, we are going to start making it more relevant for our situation. This is where customization begins. So, remember our situation is we have a chimney and it is releasing some kind of smoke. After it has gone through a certain level of plume rise del H, what is happening is that the smoke is spreading due to bulk action of wind and due to diffusion. So, here we have bulk action and here we have diffusion. Now, we can make some really nice assumptions here. So, this is x direction is in the direction of the wind y is here horizontally, laterally perpendicular to x, and then z is here pointing upward. Now, first assumption that we can make is that the bulk action due to wind in y and z direction is 0, because we have assumed our x axis to be in the direction of the wind, and we are saying the wind is unidirectional, it is not circular, it is not cyclonic or anticyclonic. We should know this is an assumption, because sometimes wind will move in circular pattern or spiral pattern when we have cyclonic or anticyclonic movement of wind. The movement of wind is also affected by obstructions to the movement of wind. So, this is just an assumption. So, the next assumption after assuming that diffusivity constants are constant in the direction, the next assumption is that wind action in y and z is 0. Bulk action due to wind in y and z direction is 0. So, right here right away these two terms will become 0. Yeah. Now, we can make more assumptions. Now, in y and z direction bulk action is 0, but diffusion is still important. So, these two terms we can't get rid of, these are important terms. Next assumption that we can make is that in x direction diffusion is not important, diffusion is much slower. In x direction the wind is significant enough that del cu by del x will dwarf dx del square c by del x square. So, what now we are going to assume is that this term is also equal to 0. Now, our system has become very simple. So, the third assumption is in x direction diffusion can be ignored. We are going to make one more assumption. The other assumption that we are going to make is that we have reached steady state. Why are we making this assumption? Because once the chimney is established, it may take few hours, minutes, even days for steady state to be established. But the repercussions of the chimneys establishing and the industries working are not limited to this short time span, but it is going to have effect over much longer time span like decades. So, if within a couple of hours or few days even maximum the steady state is reached, we are more interested in what happens during the steady state, not as the steady state is being established. Also typically the concentration of contaminant will be higher in steady state than in the pre-steady state situation. Now, what happens when we have reached steady state? Remember, at steady state dc by dt becomes 0. The net del m by del t becomes 0, that is the definition of steady state. So, now we have converted one more term here equal to 0. We have heavily simplified this equation. So, now our equation looks very simple. So, let us write down our equation. So, we have one bulk action term and we have two diffusion terms for steady state. Remember, this is happening in steady state. There is another assumption we are going to make. I am going to write it as the fifth assumption. The fifth assumption is u is constant in x direction. Now, this is not frequently true. Let us say the wind is blowing from one end of the road to another end of the road, or one end of the town to the other end of the town. The velocity of wind will be a function of both x and time. However, for short durations, for short distances or for very long distances or averaging it over longer periods of time, we can make this assumption that u is constant in x direction. What happens when u is constant? This u will come out of the derivative. So, what we will have then is u del c by del x is equal to okay. So, this is a simplified equation that we get for our model for transportation of contaminant through a fluid, in this case air, with certain assumptions. We have made at least 5 assumptions here. Now, there are other assumptions, we will discuss them in a bit, But I want you to take a look at this. When we in later classes talk about groundwater contamination, we are going to come up with almost similar model. And then how would it be different from the model that we are deriving for air? This is where very fine customization begins. We are going to integrate this model. This is a second order partial differential equation. It's a second order PDE. Personally, I am aware of more than 7 ways to integrate this, but none of them are part of the course. So, I am not going to teach you, I am just going to give you a general solution. The customization of general solution will begin by the way we put boundary conditions to it. So, the general solution for this second order PDE is given by this very simple equation. C is the concentration which is unknown, K is the integration constant, X, and then we have an exponent. X is the distance in x direction, y and z is the distance in y direction, dy dz are diffusivity constants in y and z direction. We have assumed they are constant, they do not have to be. If they are not constant, you will not get this equation. This you will only get once they are constant. So far, this system will work for most pollutant transports that behave similarly. This is where customization really gets beautiful. We are going to find out the integration constant. For a chimney that is emitting contaminant with emission rate A, which accounts for the concentration and the flow rate. So, we have flow rate of the contaminant, the smoke coming out, we have concentration. We also need to make boundary conditions here. So far it is applicable for different systems, but it is the boundary conditions that we apply which will make our solution unique to the chimney situation, chimney problem. And the boundary condition that we are going to apply is very simple. We are going to say that the net amount of pollutant emitted by the chimney, net amount of pollutant emitted by the chimney is equal to net amount of pollutant downwind. This is the boundary condition we are going to apply, and I am going to discuss this in detail in the next class, where we are going to apply this boundary condition. We are going to do double integration del y del z. Del y will range from minus infinity to plus infinity. Remember, double derivative gives you volume. So, del y ranges from minus infinity to infinity. So, we are covering the entire spans of the universe. The del z will depend upon whether the chimney has 0 height or it has a particular h height. So, this we will talk about later. This is the boundary condition we will apply. The boundary conditions will vary depending upon the kind of situation you are in. So, this is all for today. In the next lecture, we will apply the boundary condition, derive our formula, apply it to some simple situations. And this is not going to be a very simple application like you learned in some other undergrad course perhaps. If you did not, do not worry, you are learning here now anyway. We are going to look at some interesting situations where things are not as ideal as we wish them to be. We have obstructions. All right, see you in the next lecture. Thank you.